Okay, the next section is 10.2. We're going to talk about limits in motion, the area problem. So what this is integrals. So let me show you the well, first of all, we'll do distance from constant velocity, distance from changing velocity. We'll do limits at infinity, and we'll talk about how that connects to areas and integrals. So first off, here is the definition of an integral. Okay, now it might look confusing, but basically what this is if I have a graph right here, what the integral is, it's very simply the area underneath the curve. That's all it is. So what this means then, right here, is this is the y value. So what that's saying is take some change in x, like here's a change in x right here. So I'm going to call that delta x right there, and multiply it by the corresponding y value for that change of x. And what you're going to get then is a little box. You're going to get a little area. And if you take the limit as n goes to infinity, then what you're doing is you're taking more and more boxes. So you're basically shrinking the size of these boxes until they're so small that you're getting an exact area underneath the curve. Now you can write that like this, where it says take the interval from a to b, where this is where you're starting from. So if you're going to do that, let's say we start from here where this is a, and let's say we go to b right here. What that is the area underneath the curve from a to b. That's what an integral is. Okay? And what's really nice is, let's say we have a velocity time graph. The units on velocity are things like meters per second or feet per second, and the units on time is seconds. So what happens when you take the integral, or the area underneath the curve, you multiply, you get area, which is meters per second times seconds, which gives you a distance. So it turns out the integral of a velocity time function will give you a distance. So it turns out that finding the area underneath the curve can oftentimes be very useful for us. So here's an example then. Let's compute the distance traveled. So let's say a car travels on average 56 miles per hour for 3 hours and 30 minutes. How far does the car travel? Well, this is a pretty easy problem. Just do distance equals rate times time. So we can plug in 56 miles per hour in for the rate, and we can plug in the time of 3 hours and 30 minutes, but we want to make sure we pay attention to units. Since we're dealing with miles per hour, we've got to stay in hours, so we'll have to do 3.5 hours. If we multiply that, it gives us a distance of 196 miles. Now let's do that problem a little bit differently now. Let's write an equation. Let's write a velocity function. The velocity time function for this would be 56 times t, because if you look at the units, we have 56 miles per hour, and if we multiply by t in hours, the hours would cancel and we get a distance. Or I'm sorry, we wouldn't need a t here. The velocity time function is just 56. Let's look at writing a distance time function then. So distance time function would be 56 times t, because the units would cancel and give you distance, which makes sense because the derivative of distance gives you velocity. So if you take the derivative with the power rule, you just get 56 right here. So what I'm going to do now is I'm going to find the area underneath the curve. So I'll graph the velocity time function. Here's 56. It just looks like this. As time goes on, we just have a constant velocity of 56. So if I want to find the answer for distance, that's the area underneath the velocity time function, which in this case is up to 3.5. Is the area up to 3.5. So obviously to find the area of that rectangle, you just do 56 times 3.5, which is exactly what we did before, and that gives us 196 miles. Or you can do this in your calculator. You can go from 0 to 3.5 of the velocity time function 56 in terms of x, which there is no x here. But this you can do on your calculator, which I'll show you how to do in the web work homework, and this will give you the 196 as well. So there are different ways to look at this, and it turns out that some of these ways oftentimes are going to be easier, whether it's the geometry from the graph, finding the area underneath the curve, or whether it's plugging this into your calculator. But we're going to use different methods throughout the homework. The last thing I want to show you is right here. It turns out when you're finding the area underneath the curve, you can make these rectangles underneath the curve. This is called LRAM, which is the left rectangular approximation method. It's saying you're going to take boxes at specific intervals, putting the left endpoint of the box underneath the curve. There's also the right rectangular approximation method, which does the exact opposite. It makes rectangles with the right endpoint on the curve. And it turns out that if you, for example, average those together, then you can get a good approximation for the area underneath the curve as well. So there's another way to do it with a finite number of boxes, trying to find the area underneath the curve. which this doesn't make the web work homework, but we might do this on a practice quiz, and it's very easy. Obviously, you're just adding up the area of these boxes. So we might do this later if we get a chance. That's pretty much it. So let's start the web work homework and go over